Hello everyone. We are going to discuss section 6.2, the Bohr model. The learning objectives here describe the Bohr model of the hydrogen atom, and then the second one is something that might show up on a homework question, but will not be a major part of a quiz or exam, which is using the Rydberg equation to calculate energies. So I want to, before we jump into this, go back to where we left off at the end of 6.1, which was this Rydberg equation. So that is kind of foreshadowing where we're going with this, where we notice that the inverse of the wavelength times is equal to a constant times this relationship between integers. Okay. Now it turns out that that is more than just an interesting mathematical anomaly. It's the explanation for what the electrons are actually doing within the atom. So what is happening in this model is that there's a lot that was wrong with this model, and this book is doing a pretty good job of not sharing that with you. But the idea is that we have different energy levels within the atom where the electrons are located, and the electrons move back and forth between those energy levels, and as they do so, they can either absorb or emit energy. And that's what we're showing down here. So the change in the energy level, so final minus initial, is equal to some value, Planck's constant times the energy of, or I'm sorry, the frequency of the emitted light. Okay, so it's based on looking at these changes in energy levels. And so this essentially is giving us that Rydberg equation that we had seen before. So these values of N are values of different energy levels, and we can calculate the energy that is emitted as we go from one energy level to another. So this is called the Bohr model of the atom. And the idea here is that we have what's called a ground electronic state, which is where the electrons are in the lowest possible energy level. And we'll talk later in this module about what that lowest possible energy level is. And then when they are able to absorb energy, possibly by having an electric current passing through them, they absorb energy and go to what's called an excited electronic state. And this has a higher energy. But that is temporary, and they eventually drop back down into a ground state. And as they do so, they emit electromagnetic radiation. So that's what's going on in the Bohr model. Some additional mathematics here. Again, we're not going to get too much into the math here. But I want to show you this model of the Bohr atom, which is a better model than you'll see in most textbooks. What we're looking at here is the energy levels 1, 2, 3, 4, 5. So 1, and this is again specifically for hydrogen. 1 is the ground state, and you can use the Rydberg equation that we had talked about earlier to find the change in energy. And you go to 2, so this is energy level 2, so you have an excited electron up here. Energy level 3, 4, 5, and this is saying infinity. Don't worry again too much about the specific numbers on these. What you want to look at is there's a giant gap, and then the gap gets smaller and smaller and smaller. And that's one of the trends that comes up from using this equation. So if you use this equation and you find all of the possibilities, you'll see that that is how it works out. How this actually works is we have electrons that start out in the first energy level, and when energy goes into the electrons in some way, maybe again you have an electric field, they will absorb that energy and go up to the second energy level. Um, and as this happens, what is key here is to realize that they can only absorb an amount of energy that gets them at least this high. Okay, so if the energy is somewhere in here, there is not a 1.5 energy level. It has to go from here all the way up to here. Think of it kind of like if you're walking up a staircase, you don't kind of step halfway between stairs. Or if you're looking at, say, um, the spokes of or the gears on a bicycle, there's only certain gears. You have first gear, second gear. You don't have first and a half gear. It has to be one or the next. And then you have 3, 4, 5, etc. You do have these other ones that are available. So you have to go between possible levels. And this is the absorbing of that energy, and you can go even from an high one to an even higher one. So we see that over here. So that's when the electricity goes in. And then when we see the light, so when we see the line spectra, what's happening there is that all of this that had been absorbed can drop back down. And it turns out, and this is true for all pretty much all atoms, when they drop down, they drop down to the second energy level, we're able to see a color for that. When they drop all the way down to the ground level, though, that is getting into the ultraviolet, and we don't see that. Okay, this is too big of an energy gap in that the frequency, or the energy is high enough that the frequency is in the ultraviolet range as opposed to the visible range. So those colors that we were seeing from the line spectra were occurring because we're dropping down to the second energy level, not to the first one. However, those Rydberg calculations essentially still work for this. They still work for the dropping to ultraviolet. Here we're showing an example of one of those calculations. Again, though, the focus here will be more on the conceptual level, but you could see some homework with using the Rydberg equation. Okay, so again, conceptually, where this is going is we end up with electrons that can have only certain energies available to them. The name for this is quantized. Quantized means there are only certain values allowed. If you think of a staircase is quantized because it has only so many steps. The same thing is true for energy levels in electrons. So we call these quantum numbers because there are only certain values allowed. So when you think about quantum mechanics, quantum numbers, what that really means, all it means is there are only certain possibilities. Okay, so we have the first energy level, we have the second energy level, we don't have a 1.5 energy level. Okay, there's not infinite possibilities there. Only certain values are allowed. The energy of the electron is increasing as it gets farther from the nucleus. And it increases, again, one step at a time based on those energy levels. And then the lines that we see in the spectra are occurring because of those quantized electron energies. So because there's only certain values allowed, we only see certain lines that show up. This is why we see the line spectra. And the reason this is different from the black body radiation is in the black body radiation, there's opportunities for the elements that absorb, or the electrons that absorb that light, to transfer them to other gas particles, or other, I should say, other atoms via other mechanisms that that are able to spread that out a little bit. And we're not going to get to that level of detail in terms of describing that, but that's why that happens. So when we have what I like to call bulk matter, which is something like a light bulb or the sun, or your oven, where there are essentially atoms close together, you get the black body radiation. When you have individual atoms of an element by themselves, then we get the quantized line spectrum. So this is the basis of our understanding of what electrons are doing. The, I guess, unfortunate thing is that this model in the full detail here only really works for hydrogen. And we'll talk about what else is going on and why it doesn't work for other atoms, at least a little bit, in the next video.